Excellent, thank you. Yes, so I guess I should start by saying thank you to my co-authors, and you've already heard from Marcus Bainschap, so we don't need to say any more. But essentially, this data is from the Horizon 2020 program DownToTen, which was one of a number of different programs that were instructed by the European Commission to reduce the non-volatile regulatory particle number measurement method from a lower limit of about 23 nanometers down to about 10 nanometers or just below. So with that in mind, I'll go forward. Yeah, so originally we had the Horizon 2020, originally we had the PN legislation looking at diesel vehicles. And then, of course, we had the advent of GDI vehicles come along very soon after we'd implemented that legislation. And there was always a concern that there were particles that were being emitted by certain technologies below the size range that we were measuring for diesels. And although some of these are volatile, there are definitely some particles below 23 nanometers that are of regulatory interest. So DownToTen was one of these programs that was invented to actually investigate these smaller particles and a methodology for measuring them within a regulatory frame. So the measurement system is very much based upon the original PMP system. So it uses hot dilution and a volatile removal stage in order to eliminate the volatile particles and leave us just with a solid particle that's defined by the way we measure it. Now, in DownToTen, we used a catalytic stripper, and you've heard a lot about those already today, rather than an evaporation tube, which is what the 23 nanometer system in legislation currently relies on. So we use porous tube diluters instead. So this is essentially where the dilution air is pushed through the walls of a central cylinder, which stops the particles from actually impacting on the walls and makes it much easier to transmit very small particles all the way through the system and to the particle counter. And of course, we use a condensation particle counter with a lower size limit. Now, within DownToTen, we used 2 particle counters and sometimes 3 in parallel. And generally, the results that you'll be seeing will be a comparison of a 23 nanometer system, 23 nanometer CPC and a 10 nanometer CPC. But also, in some circumstances, we used particle counters or condensation particle counters with D50s lower than that, so down to 2.5 nanometers. And in one particular technology, that's quite important. So I just need to spend a little bit of time explaining the way that the data can be viewed. So you'll see this kind of colored chart many times with these 3 different regions. So in the green box, this is the region in which the current emissions limits for particles on light-duty vehicles, heavy-duty vehicles, non-road mobile machinery are complied, whether you're looking at 10 nanometer data, which is up this axis, the y-axis, or 23 nanometers along the x-axis. And data is normalized to the existing limit value. So all passenger car data is normalized to the limit value of 6 times 10 to the 11 particles per kilometer. So at 100%, and you'll see these kind of dotted lines, is compliance with the current limit value. The next region is where the limit is exceeded at 10 nanometers, but it's not exceeded at 23 nanometers. So of course, this is where the future regulatory interest lies. And then up here in this other zone, which is kind of this red triangle, this is where the limit is failed, either with 23 nanometers or with 10 nanometers. And I've also got a couple of slides where I use SPN, solid particle number less than 10 nanometers on this axis, where we're starting to look at the data that's below 10 nanometers as well. And if you see data that sits on this one-to-one line, that's basically saying that the 10 nanometer data is identical to the 23 nanometer data. And as we move away from it, and remembering this is a log scale, we are increasing the 10 nanometer data relative to the 23 nanometer data. So we did lots of tests. There's around about 260 tests where we're comparing 23 nanometer data with 10 nanometer data from a number of different partners within the program. We loss corrected the data using the dual CPC method, which David Kittleson, who's online and who presented at the Cambridge Particle meeting maybe 3 years ago. And we also have 200 results where we're looking at SPN data below 10 nanometers using 2 to 7 nanometer D50 PNCs. As you can see, that the data kind of also covers a wide range of orders of magnitude as well. So I'm having some issue moving the slides on at the moment. So we've tested a number of different technologies. So diesel vehicles, heavy duty diesel vehicles, port injection gasoline, direct injection gasoline, DI and PR and PFI hybrids, performance vehicles, mopeds and motorcycles, CNG vehicles, and dual port and direct injection gasoline vehicles with a wide range of after treatment systems on a huge range of different emission cycles, and then looking at other factors such as active and passive regenerations, different temperature tests, and things like the state of charge of hybrids. So there's a huge amount of data that lies within this, these few slides that I'm going to show you. So if we look at where we see the PN limit exceeded, whether or not it's 10 nanometer or 23 nanometer data, and this is non-DPF diesels, it's mopeds, it's high performance port fuel injected vehicles, it is Euro 6D GDIs, but those were certified to 6 times 10 to the 12 rather than 6 times 10 to the 11. Port fuel injected motorcycles, and then some Euro 6D temp diesels with DPFs, but during or just after regeneration. And we also saw some GDI vehicles of 6D temp specification, but these are ones with kind of developmental GPFs and in under very severe conditions, which the vehicle would not necessarily have been calibrated to do. But I think the most interesting thing is here that the vehicles that are giving us very high levels of emissions are the vehicles that are generally not subject to legislation at the moment. So there's clearly a gap there in the regulatory space. So now if we kind of zoom in, and you can see I've gone into this region where the limit is exceeded at 10 nanometers and not at 23 nanometers. What we and where we can see the 10 nanometer regulation is or if we had a 10 nanometer regulation, we'd be failing, but we'd be passing at 23 nanometers. And you can see this is mopeds and motorcycles, some 6B GDIs, and 6D GDIs on non-standard cycles. So what we should say is most GPF vehicles we're testing at the moment are quite young. If you add ash to a GPF, you increase the filtration efficiency, and quite a few of these vehicles would then drop into the compliance zone. So I think what this tells us is that in the future, we need to be optimizing GPFs or looking at some mechanism in the legislation that takes on board the fact that GPFs age in a positive way, which is kind of opposite to the way that we normally see after treatment systems as degrading over time. If we look at diesel vehicles, you can see we're sitting right along the 1-to-1 line for nearly all the tests. 1 or 2 are slightly above. And this is to do with the high efficiency for very small particles, diffusion driven for particle filters, and the high efficiency that we get when we have soot accumulated on the DPF. So really, we don't have very much concern about DPFs in terms of their ability to trap very small particles. But what we do need to do is take into account the fact that DPF regenerations increase PN emissions, but also ash accumulation on the DPF will give you a filtration advantage as well. So these are things that maybe the future regulation needs to take into account. And really, there is no difference between the sub 10 nanometer data and the 10 nanometer data when we're looking at diesels with DPFs. So this is some data immediately following a DPF regeneration. As you can see, we're kind of getting dangerously close to the boundary of 6 times 10 to the 11 here, and 1 or 2 tests are squeaking above. And then we have, during regeneration, we have particle emissions that are sometimes substantially above the limit. But of course, you have to take into account the average emission of that vehicle over time. And when you take that into account, DPF diesels are still well below the limit. So this is where it starts to get interesting when we start looking at gas technologies. And we're looking at CNG here. This is 2 different CNG vehicles. We see lots of tests that are compliant at PN10 and PN23, but we do start to see some that are, even with 60 temp vehicles, that are into the 10 nanometer failure zone. So CNG combustion produces very little soot, and we know that soot is very effective at kind of mopping up small solid particles in the combustion chamber. And we believe that a lot of these particles are derived from the combustion of lubricant. And so if we have a very low level of soot, those very small metallic oxide particles remain independent and may be very abundant. However, what we do see is that if you apply a particle trap, so you can see that there's some of the tests up here, we retrofitted a particle trap, and we see the particle numbers drop by a couple of orders of magnitude. So the question is it possible to achieve very low levels or low enough levels of PN from CNG applications merely by having good oil control, or do we need to fit a gas particle filter? And I think that's one of the big research questions to come in the next few years. If we start looking at PN sub 10 nanometers, and as I say, we're measuring down to 2.5 nanometers here, we see a large number of tests at 10 times or up to 30 times the limit value at 6 times 10 to the 11. So it's very clear that there's a lot of these very small particles sometimes in CNG. And we are then at a situation where we might be thinking that it's necessary, even if we can't measure these particles very well, we have a responsibility to try to control them, which means fitting a gas particle filter. The trouble is, if we look at the level of particles here, and we're above 6 times 10 to the 11, and we drop down to the level of particles that we've got at 23 nanometers, we are looking at something like, 10 to the 10 particles per kilometer. And you would have to apply a 10 to the 10 particle kilometer legislation at 23 nanometers to enforce a trap that was effective enough to control these. So this is clearly a very, very demanding question. And what we need to do is to find a way to legislate and control these particles without making it very difficult for other technologies to achieve particle control or even continue to exist. Sorry. So then we have just having a general look at the kind of fractions of particles that are present below 23 nanometers. So generally what we can see is that if you're looking at PN10 levels across all technologies, it's less than 80% of the total number of particles exist between 10 and 23 nanometers. And then if you start to look at 10 nanometer particles for CNG, it could be up to 97% of particles can be between 10 and 23 nanometers. And then if we start to look at the sub 10 nanometer particles. And I mentioned earlier that we can see that soot is or that we understand that soot is a very good kind of moderator of very small particle emissions because it mops it up in the combustion chamber. We can look at all the different technologies here at 23 nanometers compared to the ratio of sub 10 nanometer particles to 23 nanometer particles at the point at which 23 nanometer particles are greater than 6 times 10 to the 11 particles per kilometer. And basically what we see is that as you reduce the number of 23 nanometer particles, you see an increase in the number of sub 10 nanometer particles. So that mechanism by which the presence of soot allows you to moderate sub 10 nanometer particles looks to be clear in the data that we've collected in DownToTen. So where are we in terms of regulatory implications for the future? Do we need a PN10 regulation? And I would say it's highly probable for gasoline and possible for diesel. The 6D temp GDIs can sometimes extend above the 23 nanometer limit. And when we go to severe operation, so kind of off-cycle conditions, quite often we'll see exceedances. So we need better GPFs. I think if we're looking at engine out, you need GPF efficiencies of 88 to 90% as a minimum. When we consider diesels, it's only really during regenerations or just after that we have a concern. So maybe this is more about regenerating to a point where you maintain a small soot cake to give you high filtration efficiency rather than completely emptying the DPF with a regeneration. So maybe this is a strategy issue rather than a filter substrate or an approach issue. But then if we talk about PN for sub 10 nanometers, it looks like this could be necessary for CNG and maybe for other gaseous fueled applications as well. We can see particle emissions of at least 10 times the emissions limit for 2.5 nanometer particles. But we do see that if you just take a standard GPF and apply it to a CNG engine, it is very effective because it's very effective at collecting particles through diffusion mechanisms. So we just need a mechanism by which we can force those filters to be fitted to gas engines, and we should be able to solve the problem. What we don't want to do is to keep the 23 nanometer limit. And because we're expecting at Euro 7 to see technology harmonization, i.e. the same limit values for all technologies, and therefore the most demanding technology will define the limit value, we could be in a situation where we would need a very low limit value for all sorts of technologies in order to force that filter on the CNG application. So I think that's a very interesting perspective and again, another important area for future research directions. Okay, and that's my last slide. I would say if you're interested in the presentation, you'll obviously get this passed to you by Combustion at the end. I'm happy to answer some direct questions, but you can also go and dig deep into the DownToTen website and see the very, very interesting activities that we've been doing. And it's much broader than just the data that I've shown you. So I'd encourage you to take a look and see what you can find. Thanks for your attention.
Great. Thanks so much, Jon. I appreciate that. So Amaya is the first to ask a question. We'll take a couple of these before our break this afternoon.
Sure, go ahead.
Hey, Jon, this is Amaya. Thank you so much. Excellent presentation. Quick question. I think you said that you've measured this down to 0C in terms of temperature. And I believe future regulations will go down to -7C. Obviously, emissions will go up at lower temperatures. And I was just wondering if, A, you have plans to go down to measure to -7C, and then what do you expect in terms of the fraction or the relative emissions at 10 nanometers and 23 nanometers? How would this plot change?
Yeah, I mean, it's an interesting thing. So we did do some tests down to -7. And under some circumstances, you produce, because of the heating strategies, because of the catalyst heating strategies, you produce an awful lot of soot. And so, for example, in gasoline applications, we saw a lot of soot being produced, and that soot essentially reducing the numbers of sub-23nm particles that we were seeing at the same time. And so cold start sub-23nm particles were then reducing relative to the warmer temperature ones. It is definitely an interesting area, because we know that we're going to be combining in the future, under the kind of Euro 7 regime, more stringent operating conditions and maybe more stringent thermal operating regimes as well. So there's a whole series of changes that we're going to see, and challenges for particle control.
Great, thanks. We'll take one more question from Felix, and I see that there are a couple other questions that are out there, so maybe we can have another discussion in the chat during the break, just to give people a bit of a rest from this and some time to stretch their legs. So Felix, go ahead.
Jon, thank you very much for an excellent presentation. I was particularly interested in your results from the CNG vehicles. Mm-hmm. I wondered if you could just comment a little more on perhaps why you don't see those particles from gasoline, acknowledging your point about the lubricants, and also whether there's any work on the composition of those particles, because obviously not all particles that we breathe are equal regardless of their size.
Yeah. Well, so, I mean, we do believe that we see them from particularly port fuel injected vehicles. There appears to be a kind of threshold of soot at which you get a large degree of suppression of those small particles being around independently, and that is kind of, you're on the slightly more favorable side with gasoline direct injection, and you're on the kind of the other side with port fuel injection. And we've seen some very high level emissions from some port fuel injection applications, particularly motorcycles. But I'm guessing that motorcycles don't have quite such good oil control in some circumstances, and therefore it's a combination of that effect and the amount of oil that's being consumed. In terms of health effects, I mean, maybe we should be really concerned about these small particles. I mean, we know that the kind of sub-20nm particles do get translocated within the body. They do get concentrated in some of the organs. And we know that metals of that size have interesting biological, interesting in quotes, biological activity. And so maybe these are things that we should be even more concerned about than the carbon particles. But I think at the moment we don't have a particularly good steer from the health effects people on that. But I think you know, it's clearly an incentive to put traps on all applications where those particles might be present, just as a precaution.
Great. Well, Jon, it looks like you have a few questions in the chat as well, so you might have a busy break if you.
Okay. Okay. Thanks.
But with that, I would like to thank all the speakers from our first section. I think it's been going quite well. With that, I will hand it over to Adam to say a few words before the break.
Very few words. Just we'll take a 5-minute break and be back at 3:10 British Summer Time. So see everyone in 5-6 minutes.